So we've just finished in our previous class getting an introduction, first introduction to what derivatives ought to mean for functions of several variables. And yesterday that took the form of the partial derivatives. These are ways of taking a derivative of a function of several variables where we're treating only one of the variables as a variable and treating all the other ones as though they're constant, right? So if we take a partial derivative with respect to y, then we're treating x and any other variable that might be involved in that function as though they are constants and only letting y vary, right? And if you remember, the interpretation of what we're doing there is that we're slicing the graph of our function of several variables to take a trace in a vertical plane with a constant value of one of our variables, and then looking for a slope of a tangent line to that trace, and calling that slope, that instantaneous rate of change, the partial derivative in that direction. So if this surface here is the graph of my function f of x and y, then if I take a slice of this graph at a constant value of x, so in this example, this red curve here looks like it might be a slice with the value of x that's x equals 1.75, right? So that vertical plane x equals 1.75, we'll put that on our picture here real quick, right? When that vertical plane slices my graph, we get this trace, right? This curve, and a slope of a tangent line to that curve, that's this green line that we can kind of see here. If we look at this sort of straight on, the slope of that tangent line would be the partial derivative with respect to y, because we're treating x as though it's a constant, but we're letting y be the thing that varies, right? And conversely, if we hold y to a constant value and take a slice of this graph in a plane where that y value is constant, then the slope of that tangent line will tell me the x partial derivative. So our job for today's class, our goal for today, is going to be to try and put those two pieces of information together. So what can we do jointly with the x partial derivative and the y partial derivative at the same time of a function of two variables? And that's going to take sort of three different forms as we go through the day today. The first of those forms is going to be to find an equation for a tangent plane to the graph of a function. So a tangent plane is going to be exactly what it sounds like. It's a plane, first and foremost. So we remember from our previous chapter how to find equations for planes if we know a point and we know a normal vector perpendicular to the plane. And that plane is going to be tangent to the surface, which is the graph of this function. So in particular, the tangent plane is going to contain as a subset both this tangent line in the x direction and also this tangent line in the y direction, right? And that's actually how, at the beginning of our class today, you are going to discover how to find an equation for a tangent plane by insisting that it contain both of the tangent lines in the x direction and in the y direction. The challenge, I think, is going to be to figure out how the slopes of those tangent lines as single numbers which represent the partial derivatives with respect to x and y can be used to determine direction vectors for those tangent lines in 3 space, that we can then use those direction vectors in 3 space to determine a normal vector to our tangent plane. So that's the first disguise that our joint use of the x and y partial derivatives is going to wear today. The second is called linearization. And the idea behind linearization is that we can use a tangent plane to the graph of a surface as an approximation for the surface itself. In other words, for a function that is sufficiently nice, so for a function which has continuous first-order partial derivatives, the linearization, the tangent plane, gives us a surface that approximates, as well as any plane can approximate, the shape of the graph that's underneath it. So we can use that plane to approximate the values of the function itself in points that are nearby to the point of tangency. Just like in single variable calculus, you can use a tangent line to approximate the value of a function near its point of tangency. And finally, we'll talk about the multivariable calculus version of the chain rule. And this is really where we have to kind of come to grips with using all of our partial derivatives of a given function at the same time. Because the chain rule tells us how to take a derivative of a composition of two functions. And when those functions can both have several variables and also output several variables, right? They can be both vector valued and they can be functions of several variables. Then that means that there's a variety of different ways in which one of the inputs to that original original function, after it kind of gets processed through two different functions, might affect the output of the ultimate function, right? And so the chain rule in single variable calculus is very sort of direct point A to point B. The value of x determines a value for g of x, and that determines a value for f of x, and it's just a single sort of straight line. Whereas in multivariable calculus, there can be a lot of different pathways from input to output. And so the multivariable chain rule takes into account all of those different pathways from input to output. And so we need all the different partial derivatives of the functions that we're composing together. And for those of you who are either taking linear algebra with me this summer, or have taken linear algebra, or at least had some exposure to matrix operations in the past, I want to also present a viewpoint on the multivariable chain rule that uses matrices to represent the calculation. For me, that was kind of the viewpoint that ultimately made the multivariable chain rule click for me. But it didn't happen until graduate school for me. And I still have vivid memories of my first year of graduate school, my differential topology professor telling all of us in the class as first year grad students, you all have an unsophisticated understanding of the chain rule, because we were all sort of botching these calculations in differential geometry and topology. And the reason was that we didn't understand what the derivative of a multivariable function really is, in the sense that we're going to think about it when we talk about the multidimensional chain rule today. Thinking of the derivative of a multivariable function as a matrix or as a linear transformation. Formally speaking, it's a linear transformation from a tangent space of one surface into a tangent space of the other surface. And so we can represent that linear transformation with a matrix, and the components, the entries of that matrix, are exactly the partial derivatives of the component functions. So that's the spoiler for how we think of the chain rule. Once we think of derivatives of multivariable functions as being matrices, then the chain rule in multivariable calculus looks exactly like the chain rule in single variable calculus, that the derivative of f composed with g is the derivative of f multiplied by the derivative of g. It's just that when those derivatives are matrices, that multiplication is matrix multiplication. When they're single scalar quantities, like in single variable calculus, that's just ordinary multiplication of real numbers. So that's the roadmap for today. It's all about taking partial derivatives and using them in concert rather than one at a time.